Good morning, everyone. Myself, Dr. Brijmohan. Today, I will discuss about the DFT calculation by Radix-2 method. So, what is fast Fourier transform? It is simply an algorithm that computes the discrete Fourier transform of a sequence in a fast manner. So, let us discuss about Radix-2 FFT DIT method, where DIT is decimation in time. This is basic butterfly diagram for a sequence having two elements, say x0 and x1. So the basic operation for this butterfly is capital X0 is equal to small x0 plus x1. This will come by following the path x0 to x1 multiplied by the twiddle factor, and after adding these two terms we will get the Fourier transform of small x0. Similarly, for the Fourier transform of x1 we will follow these paths. Here x0 plus x1 into wn r multiplied by -1 gives capital X1 is equal to x0 minus x1. This is an example of a sequence having four elements. Here, for decimation in time, we convert the input by bit reversal rule. So after applying bit reversal rule, the inputs are x0, x2, x1, and x3. These are the twiddle factors for the butterfly diagram. So again, we follow the same operation as we discussed in the previous slide. Here, the butterfly involves two steps. In first steps, we will get four outputs, which has the value here, 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 and here. After this, we will start the second stage and follow the following figure so that we can obtain the Fourier transform of given bit reversal inputs. Here we see that the inputs are in bit reversal order while the outputs are in normal order. This slide represents the butterfly diagram to calculate the DFT using Radix-2 method. Again, the inputs are arranged in a bit reversal manner, while the outputs are arranged in the normal order. Different twiddle factors has been assigned for the three steps. For example, here we have a sequence having number of element 8, that is capital N is equal to 8. So the twiddle factor becomes W08, 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 W08. Similarly, W08, W28, W08, W28, and finally W08, W18, W28, W38. So after performing all the operations in three states, we will get the Fourier transforms of the input signal. This slide represents the twiddle factor calculations. Here we can see that to calculate or to evaluate the value of W20 or W12, it comes just by moving to the clockwise direction. This axis represents the real axis, this one is the negative axis, this one is imaginary axis, positive imaginary axis, and this one is negative imaginary axis. So the value of W02 is 1, value of W12 is -1. Similarly, when a sequence having four elements, we can calculate different twiddle factors like W04, W14, W24, and W34 by moving clockwise directions. And the same operation has also been applied for a sequence containing 8 elements. This is the algorithm to calculate the DFT using by Radix-2 DIT FFT methods. The basic forms or basic steps involved in the algorithms are: first we will check the length of the input, that is capital N. After this, we will split the capital N into two equal parts, say even and odd, as discussed in the Radix-2 method. Third part contains the calculation of the twiddle factors. Fourth one has been employed to calculate the FFT of the given signal. So this is the basic Python code for a sequence having 4 elements. Here we see that we have just import NumPy as a library. These sections represents the creation of FFT Radix-2 function. This section involves the splitting of the sequence into 2 equal parts. This section again represents the calculation of FFT using Radix-2 method. So when we have the local function FFT Radix-2, so we can use this function to this program to calculate the FFT of a sequence such as 1, 2, 3, 4, etc. And finally, we have printed the result. Here, we have taken an input sequence such as 1, 2, 3, 4, and after running the program, the results or of the input signals is this one. So to verify the results, we will use the FFT command. Here FFT command is a kind of global command. It is 2-line program. Here we just import the NumPy and give the input of time domain, that is 1, 2, 3, 4, and apply the command np.fft.fft to the input signal X. And finally we print the capital X, which is the FFT of small x. So again, we have the same results as we have obtained in the previous program. In this way, we can say that both programs are well matched. Thank you so much.